am Kuba. Welcome back to Bielik Anatomy. Last episode we gave our model a sense of time with rope. Today we are going to hit a massive memory wall. I will show you exactly why standard attention breaks and how to fix it by coding flash attention in Triton. Before we talk about memory, let's look at what we are actually trying to compute. The math of standard attention is elegant and fits in 3 lines. First, we compute the scores. Next, we get our attention weights by running Softmax on each row. Finally, we multiply those weights by our values. Mathematically, it's beautiful, but when you try to run this exactly as written on a GPU, things fall apart. Let me show you why. Look at what happens in the hardware. S is an n by n matrix. For a 2000 token sequence, that's 4 million floats. The GPU computes S and writes it all the way out to HBM. Then it has to read it all back just to run the softmax. Then it writes P, another n by n matrix, back to HBM. Then it reads P and V back in for the final multiplication. It's a massive traffic jam. The GPU cores aren't doing math. They are just sitting and waiting for the data to travel back and forth from main memory. Attention isn't slow because of the calculations. It's slow because of the memory bottleneck. So how do we fix it? We stop talking to HBM. You already know the GPU memory hierarchy from our previous episodes. You know SRAM is our tiny, screaming fast workspace right next to the cores. So watch this. Flash attention flips the script. Instead of computing the massive n by n matrix, we cut Q, K and V into small blocks. We load a block directly into SRAM, compute the attention scores for just that block and update our final output right there. The full score matrix never gets written to HBM. It never even exists entirely at one time. But to make this physical trick work, we need a mathematical trick to compute softmax in chunks. That's the online Softmax algorithm. Now let's write this in Triton. We'll go through the inner loop line by line, and we'll put the exact math equations right next to the code, so you can see the online Softmax algorithm in action. We launch a 2-dimensional grid. One program per query block. We map our Q heads and KV heads for grouped query attention and initialize our running state, maximum, sum, and output accumulator, all in float 32. This is the crucial load. Q comes into SRAM once and stays there for the entire inner loop. We iterate through K and V blocks. We load K, compute the dot product and scale it. This happens entirely in SRAM using tensor cores. If we are on a diagonal block, we apply the causal mask. Setting future positions to negative infinity means that they will get 0 weight after the exponential. Now the online softmax magic. Find the maximum score in the block. Compare it to our global maximum and keep the larger one. Compute the unnormalized weights for this block. Here's our correction factor. It encodes exactly how much the maximum changed. Rescale our old running sum by alpha and add the new weights. Load V, apply the exact same rescaling to our output accumulator and use a fused multiply add instruction for P times V. After the loop finishes, we divide by the final sum L to normalize everything. Then we cast back to BF16 and write it to HBM. Think about that. We just computed full attention and we only did one write to HBM per query block. So did all this SRAM gymnastics actually work? Let's look at the numbers. I benchmarked 3 implementations, our Triton kernel, plain PyTorch and PyTorch with torch.compile. Look at the sequence length scaling. For short sequences like 128 tokens, everyone is relatively close. The data fits in cache anyway, so the overhead of tiling hides the benefits. But watch what happens as we stretch the context window. At 4096 tokens, naive PyTorch drops to about 3.4 teraflops. It's completely suffocating on memory transfers. Torch.compile is smart. It fuses operations and prevents some kernel launches, which bumps performance up to nearly 16 teraflops. But it cannot fix the fundamental math. That n-squared score matrix still has to exist. How about our flash attention kernel? It rips through 65 teraflops. That is a 4 times speedup over compiled PyTorch and almost 20 times over the naive version. The compute cores are finally being fed data fast enough. We see the exact same story when scaling the number of attention heads. But teraflops isn't the number that matters most for the Bielik. The real metric is memory footprint. Look at the 8000 token sequence. Standard attention gobbles up nearly 7.8 GB of memory just for the attention mechanism on my 16 GB card. Our flash attention kernel, it runs exactly same 8000 token context using just 65 MB of peak memory. We turned an impossible ON² memory problem into a lightweight ON solution. And that means Bielik can actually use its full context window. Let's quickly recap what we just did. We implemented flash attention from scratch using the online Softmax algorithm to keep our calculation in fast SRAM and bypass the main memory traffic. By doing this, we shifted the bottleneck from the memory capacity to pure compute capability. We literally turned an out-of-memory exception into a problem for just feeding the cores fast enough. All the code, including the benchmark, is on my GitHub. Grab it, run it on your own GPU, and let me know your numbers in the comments. Next time we move to the second half of the transformer block. We are implementing the SwiGLU activation for the feed-forward network as a custom Triton kernel. Thanks for watching and see you next time. Bye!